Hi everyone, welcome to week 8. I'm back with my videos because I know you just missed them so much. This week there are more formulas because, as you know, chapter 11 is mostly about different formulas for different shapes. But this lesson is 11.5 and it focuses on areas of regular polygons. So there's going to be a lot of new vocabulary and a lot of good practice problems that you could do from this video. So to start, all polygons actually have a center. And the center of the polygon is actually the center of the circle that is circumscribed around that polygon. The radius of the polygon is the radius of the circumscribed circle. So if I start at the center of the polygon and I draw in this line segment to one of my vertices, I actually also create a radius of this outside circle. And that radius bisects the angle at its vertex. Then we have this new term, this apothem, or some people say apothem. I say apothem. An apothem is like a median and an altitude. It starts at the center, and it is drawn perpendicular to the side of the polygon. So you'll notice when you draw on these two radii, you basically create an isosceles triangle because you know all radii are congruent. Now you're going to come in and you're going to draw in this altitude or this median, and you're going to bisect the side of the polygon and also create a right angle. Now, depending on the different polygon you have, these angle measures out here are going to change, but this will always be 90 degrees here. And if you were to actually inscribe a circle inside of this polygon, so it's not drawn here, you would actually know that this apothem is the radius of that inscribed circle. And just like these radii are all congruent, all the apothem in a regular polygon are congruent to each other. So there is a formula to find the area of any polygon. So it's actually at the bottom of our notes. So I'm going to actually skip down to the bottom. So general formula for area of a regular polygon. The area is equal to 1/2 times the apothem times the number of sides times the side length. Now, if you notice in this picture, the number of sides is 6. And if you knew the side length and you multiplied by 6, you actually just found the perimeter of the polygon. So you're going to see a lot of times, you're not going to see number of sides times side length. You're going to see 1/2 A times P. And P stands for the perimeter of the polygon. So if you do 1/2 times the apothem times the perimeter of any polygon, you will be able to find its area. Now I'm going to jump up one because a hexagon actually has a very specific formula you could use. You could use this 1/2 apothem times perimeter. Or if you think about it, if I was actually to draw in all of these radii, I would create 6 triangles, specifically 6 equilateral triangles. So not only are they isosceles, but in a hexagon, they are equilateral. So we've talked about this in office hours, and we derived this formula for an equilateral triangle, and I told you it was coming back, s squared times radical 3 divided by 4, where s is the side length. If you have this formula and you have 6 equilateral triangles in a hexagon, you could take this and multiply by 6, and you'll get the area of that hexagon. So in a hexagon, only the radius is equal to the side, and that's why we have an equilateral triangle. So you can either use this formula or you can use that formula. It all depends on what you prefer and what's given to you as well. If you're given the apothem, you're probably going to want to use this formula. If you're given the side, you probably want to use that formula. So these are your 3 formulas you're going to be using in 11.5. So now we move on to the practice. So I'm going to give you a chance. So look at number 1 first. You are given a hexagon inscribed in a circle, and the area of that hexagon is 12 root 3. See if you can use that to find the circumference of the circle. Okay, so you'll notice that I drew in the center, and I actually drew in the radii as well to create an equilateral triangle, because remember, a hexagon is 6 equilateral triangles all put together. So if I know the area of the hexagon, I'm going to set it equal to my 6 times in my equilateral triangle area formula to solve for s. So, if I divide by 6, I get 2 root 3, times by 4, I get 8 root 3. These root 3's actually cancel each other out. And then if I take the square root, I'm going to find that the side of one of those triangles is 2 root 2. Now that side also acts as the radius of my circle. So now if I want to find the circumference, I could use my 2 pi r. In this case, r is 2 root 2. And to write this in simplest form, it is going to be 4 pi root 2. So that's actually how you write an answer when there's both pi and a radical in it. And then if you were to actually simplify this, it would be about 17.8 if you round it to the nearest tenth. So let's look at another problem. This time we've got the opposite. The circle's on the inside and the hexagon's on the outside. So if the circle area is 900 pi, see if you can find the perimeter of the hexagon. Okay, so the first thing that I did is I knew that the area was 900 pi. So I used my area formula, pi r squared, to figure out that the radius was going to be 30. And be very careful. This picture and this picture are different. So while this is the radius in that picture, when the hexagon is on the outside, now that becomes the radius of the circle. So the apothem acts as the radius. So what I did is I drew in the apothem, and by drawing in the apothem, I not only get the radius, but I also get a 30, 60, 90 triangle. So if 30 is across from 60, then that means I'm going to need to divide by root 3 in order to determine this piece right here. And if I do that, I will get 10 root 3. And I know that if that's 10 root 3, then that segment is also 10 root 3. So the side of one side of this hexagon is going to be 20 root 3 total. So now if I want to find my perimeter, I have 6 sides times that 20 root 3, and I will get 120 root 3 for my perimeter. So just watch out. Depending on which shape is on the outside, the radius of the circle will change. All right, now we're going to move on to some equilateral triangles and circles. So we've got a circle inscribed an equilateral triangle with a radius of 6. See if you can find the area of the equilateral triangle. So, if you remember from office hours, I drew this diagram in, and I said, when you draw in the radius of this inscribed circle, and you draw in this segment here from the center to the vertice of the equilateral triangle, you get a 30, 60, 90, because this whole angle here is 60, and then it gets bisected. So if the radius of this circle is 6, then I need to figure out what the side length is going to be. So since that's across from the 30, I know that this piece here is going to be 6 root 3 because it's across from the 60. And if I was to create the same image over here, I would have another 6 root 3. So the complete side of this equilateral triangle is going to be 12 root 3. So I'm going to use my equilateral triangle area formula, which is s squared, so 12 root 3 squared, times the square root of 3, so just watch out for the double square root of 3's, all over 4. So if I do the squaring part first, I'll get 432 root 3 over 4, and then divide by 4, and I will get 108 root 3 as the area. Okay, number 4, flipping the diagram around. Now the triangle is inside the circle. So we know the apothem of this equilateral triangle is 4. See if you could find, now be careful here, the area outside the triangle but inside the circle. So this is like a shaded area question, except it's not shaded. They're just telling you to basically find these pieces here. What's the total area? So again, I drew in my apothem, which is 4, and I drew in this radius of this circle. And using my 30, 60, 90, because it's an equilateral triangle, I'm able to deduce that that's 4 root 3. Therefore, that piece is 4 root 3. So the whole side is 8 root 3. And I was able to find that the radius of the circle is 8. So now this is where I need to plug into my formulas. So for the area of the equilateral triangle, I'm going to do the side squared times root 3 over 4. And when you simplify all of that, you will get 48 root 3. And then I'm going to find the area of the circle. So pi r squared, in this case, r is going to be 8. So 8 squared, which is 64 pi. And now if I want to find the area outside the triangle, but inside the circle, I need to take the area of the circle, which is 64 pi, and subtract out the triangle. So if they ask for an exact answer, that's what you would put. But if you have to round, let's say to the nearest tenth, it would be 117.9. Last but not least, we're going to incorporate some squares. So given the circle with a radius equal to 6 inscribed in square, see if you could find the area outside the circle but inside the square. So when you're trying to find the area of a square, squares can also have apophthegms. So in this case, 6 is the apothem of the square. And when you draw in this segment to the vertice of the square, you'll actually create a 45, 45, 90 triangle. So equilateral triangles are 30, 60, 90. Squares are 45, 45, 90. So if the apothem is 6, then this piece here is 6. And this is congruent here. So that's also going to be 6. So now I know that I have a side length of 12 for the square. So if I want to find the area of the square, that's just the side squared, in this case, which is 144. And then if I want to find the area of the circle, well, that apothem, 6, is actually acting as the radius of the circle. So you would have pi times 6 squared, which is 36 pi. And now to find the area, I have to do the square minus the circle. And if they ask for an exact answer, that would be what I would get. But if I needed to round, I would get about 30.9. And that is how we are going to use our equilateral triangle, regular polygon formula, and our hexagon formula to answer these types of questions in 11.5.